Any questions? The problem that last problem that you had there. That was a ball was initially,
Putting out more similar uniformly along the.
okay, all right. All right. So again, another cake problem. A ball is starting upwards near the surface of the earth, initially at 40 meters per second. How long until the ball is at its peak? And the answer is?
Don't we need more information?
Why do you say that?
Well, we need, I believe, 3 components to use a cake problem,
Yes.
and we've only been given 1.
Which is one of the reasons I'm doing this problem. There are actually 2 things not written explicitly, but implied by the problem.
I was gonna say, is it like the initial position is 0, like before you throw it?
You can make the initial position 0. Ultimately, we're gonna try to find displacement, so what the initial position is doesn't really help us here. All right, so first off, what are the 5 quantities that we would really like to know?
Velocity initially, velocity finally, displacement.
Acceleration.
The order is irrelevant, but I'm a creature of habit. All right, so what do we know?
The velocity initial
Is,
40 meters per second.
you good with 40 meters per second? Okay.
Final velocity 0.
That's one of the implied pieces of information, because we're talking about the peak. At the peak is the point where it turns around. It stops just for an instant before it starts coming back down. So 0 meters per second. And one other piece of implied information.
Acceleration,
Yes.
negative 9.8 for gravity.
All right, let's work on the wording here. Say it again.
Acceleration is negative 9.8. It's negative 9.8.
Meters per second.
Like you mean it,
Meters
Judy.
per second.
Meters per second squared.
There we go.
Yeah.
Why negative?
Because it's going the opposite direction of initial velocity.
Ah, okay. So why is the initial velocity positive?
Because it's moving,
Not the reason.
because you're moving away from the starting.
Not the reason. You are diminishing, Ali. Why is that positive?
Because we said so. Or
Oh,
you-
specifically,
Yeah.
blame him. When you said 40 meters per second, and I said, you're good with that, and you said yes, at that moment right there, you established up as positive. If you had said negative 40 meters per second, that would have been fine too. But as soon as that was established, up became positive. And therefore, as Joey said, down would be negative. So negative 9.8 meters per second squared.
How do we come out with that?
That's what he said. Yeah, just because he said it though, no, this one's a little bit more established. Why 9.8 meters per second squared?
So gravity, that's working down against the,
Say it again?
it's gravity, that's working down against the ball,
What is gravity anyway?
what the earth does.
What the earth does? Is that what you said?
Yeah,
Is it? Is it really? Does anything else do gravity?
I think the moon does gravity, just like, I mean, it doesn't do it as good as the earth did gravity. Jupiter, now that has an A+ for gravity. That one has a lot of-
Sun's a little bit better than that.
Oh, so-
What about me? Do I do gravity?
Gravity does you.
One thing you'll find in physics is that humans are objects.
I see.
So if Earth does gravity, is there a reason I wouldn't do gravity also?
Would assume not.
You would assume there is no reason?
No,
You would not assume there is a reason.
I would assume that, that you would not, do gravity as.
Because I'm special as a human?
I don't think the earth does gravity either, I think it's just a universal force.
All right. As we'll get into, first off, part of it is nitpicking the language. Gravity is a huge topic, of which we will study tiny little bits of it. One of the bits we're going to do is the acceleration due to gravity, which near the surface of the earth is that number. This is where it comes from. If I dropped an object, that would be roughly the acceleration. On Mars, it's 3.5 meters per second squared. On Jupiter, it's, I think, 24 meters per second squared. I forget what the sun is. We will also deal with the force due to gravity, otherwise known as weight, in a lot of our cases. And then there's the gravitational constant. So those are basically the three aspects of gravity that we will deal with. So if you notice in the other room, there's that sign that says there's a little g is not gravity. Little g,
because that's free fall.
first off, little g is a positive number. It's a scalar. This is the acceleration due to gravity. And it is not a constant, but it is close enough to a constant when you're near the surface of a huge body like a planet or moon. So the requirement to have some gravitational pull is the fact that you have mass. So yes, each of us does gravity also. Just not particularly well. All right, so in this particular case, just from a notation point of view, the acceleration in this case, since up became positive, so let's just go ahead and make that permanent, just at least making us do it. This would then be negative g. In the lab, you should not be using 9.8 because we have something more specific here. In Winston-Salem, it's about 9.798 meters per second squared.
We actually have our own, like, subscript.
I created one.
Um,
For Earth, average, the bar just means average. Earth average is 9.805 something. So if you see 9.81 for G, that's just the world average. That is not specific to Winston-Salem.
So Winston-Salem has a different gravity than the world?
Different gravitational acceleration than other parts of the world. So if you're in manufacturing and you order, let's say, 1,000 pounds of titanium dioxide, just because it's 1,000 pounds from the place that you ordered it, doesn't mean it's 1,000 pounds when it gets to you.
Oh, wow. So would we be getting more or less?
Depends on from where you ordered it and to where it's going.
Singapore to Winston-Salem?
I don't know Singapore specifically. The lowest value that I found, North Pole, South Pole were very low. No, those are the high spots. Mexico City is one of the lowest ones.
Would it get lower, the closer you go to the equator, just because it's bigger?
It'd get lower, yes, the closer you go to the equator. Because it bulges out, so you're a little bit farther away from the center of gravity of Earth.
All right.
All right, so, a couple lessons here. One, acceleration of gravity is relatively constant when you're within this when you're close to the surface of a planet. Two, it's not really constant. There's a different value at the top of this building than the bottom of the building. But to notice that difference, you need multi-million-dollar equipment. And 9.8 is good enough for a problem if it's taking place near Earth. Meters per second squared. All right, so we now have questions before we actually solve this.
So for like questions on the master set, we would imply that 9.8 is the gravity, like
The acceleration to gravity.
acceleration due to gravity.
Unless it's, generally you assume it takes place on Earth unless it explicitly says otherwise.
No, it says, from 100 meters.
Yeah, because it is a well-known fact that the Earth is the only place in the entire universe that has a building.
Okay.
Except for the problems where I put buildings on Mars or Venus. You know, for Venus, the hydrochloric acid proof buildings. Of course, it's sulfuric acid.
I think it's the second one.
It's what?
I think it's the sulfuric acid.
Sulfuric, okay. Okay, so in order to solve these, once we've established acceleration is relatively constant, which is going to be true for these type problems, we need to then figure out what equations we're working with. Obviously, constant acceleration kinematic equations. Can anybody name one without looking?
I've already looked. Oh, I can do it off memory.
At this point, can you do it off, how many can you do off memory?
Oh, not many.
Oh, well, give me one of them.
Velocity equals, velocity thing.
Thank you very much.
equals, change in position over change in time. Velocity equals, in the top half of it, you would do,
In the numerator?
in the numerator, right? You would do initial velocity, or final velocity minus initial velocity over time. How we do it?
T or delta T, whichever way you want.
And
I'm not commenting on correct or not, we'll worry about that in a moment.
And then change in position
Okay?
equals initial velocity plus half acceleration time. Yeah, that's all I got.
All right, so there are a couple issues here.
Okay.
What are the units of change in position? What are the international standard units?
Meters,
Yes, what are the international standard units of velocity?
meters per second.
All right, so there's gotta be something wrong here if that's meters, if that term is meters and that term is meters per second. All right, international standard units of acceleration?
Meters per second squared, so time squared.
There we go. All right, so that one's done. That is one of the cake formulas. This one right here, what would the units of the right-hand side here be?
Units of the right hand system.
Or what about the numerator? What are the units of VF minus VI?
Meters per second.
All right, and units of time? So if I have meters per second divided by seconds, what do we end up with?
Meters.
GG?
Meters per second squared.
Yeah. Meters per second divided by seconds is the same as meters per second times 1 over seconds, which is a meter over second squared. Therefore, what is this a formula for?
Acceleration.
Yeah. More specifically, average acceleration. And this one right here is average velocity.
Oh, then the one for, average velocity, so the second one for it would be, final velocity minus initial velocity over. It's a number. What's the number?
Pi,
No.
73. You thinking over 2?
Yeah.
Now, what you just said was average velocity
Right.
is equal to, I think you said VF minus VI over 2.
Yeah.
Anyone want to correct that? Units work out at least. We're averaging here.
T or time after?
Oh, no, not time involved here.
Plus.
Yes.
That's wrong.
You're averaging, you add, divide by what you got. All right. This is definitely using one of the cake formulas. Jack threw in an extra letter. If we multiply by time, what do we get?
Something.
That is true, something.
Oh, we get, change in position.
Yeah. All right, so we got another one here, because when you're looking at the cake formulas, we have 2 that are for displacement or change in position, whichever wording you like. So this is one of them, and the other one is VI plus VF over 2 times time. All right, so we've got that one right there. So it's just average velocity times time. And the other 2 start out with final velocity.
Oh, final velocity squared equals initial velocity squared plus 2 acceleration, times, the change of position.
All right. I appreciate your putting yourself out there like that. Let's nitpick some of the language. He said final velocity squared equals initial velocity squared plus 2 times the acceleration. I don't know if you specifically mentioned the dot. It's dot multiplication or dot product with displacement or change in position. What's wrong with that language?
Is it 2 acceleration, like 2 acceleration dot position changing?
That's not it. No, it starts out, what is this, VF?
Oh,
The final velocity.
Ooh,
The magnitude
otherwise known as? Yes, except without the question mark. Say it again. Yeah, that's speed. It's final speed squared equals initial speed squared. Oh, that's all. Yeah, no vector symbol.
oh, okay, I see.
All right, we got one more. Since we have 2 that start with displacement, well, we have 2 that start with VF, or Yeah, there's a VF there. And the last one, this is velocity. And it comes from that equation.
What did we do?
It was the first one.
Oh, got it. Final velocity equals initial velocity plus acceleration times time.
There we go. All right, so we got our 4 cake formulas, and then we have some additional ones right here. All right, so we are trying to find how long. So what are we trying to find?
How long?
The question is time or displacement?
Oh,
Time.
Okay, I did have a student a couple years ago, who had been in this country, I think 5 years, and to her, every time she saw the word long, she thought distance. Understandable. I put down how long here to indicate time, as is, I think, traditional US vernacular. However, if you see the word long and you immediately think displacement, again, I try to work on that when I'm writing problems out on tests and quizzes, but still not always successful in that one. All right, so which formula do we use? Let's just go ahead and label these as A, B, C, and D.
D.
Which one? Said C?
D.
D.
I would have to concur, I think.
If in doubt, if you're not sure, we know these 3 things. We're trying to find time. Displacement is not really part of this first question, so therefore we want the equation that doesn't have displacement in it. So plugging in, we get 0 is equal to 40 minus 9.8 t. And now we've reduced this physical problem to a math equation. And it's just solved. I'm gonna bring this over to the other side.